If n is a submanifold of M, whether embedded or an immersed submanifold, then for every point P in N, the tangent space to N at P is gonna be a subspace of the tangent space to M at Fp. Why is that? Well, remember in the definition of both immersed and embedded submanifold, we require that this structure map be an immersion. And what does that mean? That just means that the corresponding map on tangent spaces, this differential, is always injective. So under this injection, we can view this tangent space of N as a subspace, as a tangent space of M. Now we want to ask, so how do we describe the tangent space of N inside of M? More specifically, which vectors inside this tangent space of M actually lies in the tangent space of N? And to answer this, we're going to give three descriptions of this tangent space, TPN, inside TFPM. This first description is going to work for all cases, embedded and immersed submanifolds, but the second description is only for embedded submanifolds, the second and third description. These three descriptions correspond to the three different ways we can view vectors, tangent vectors. Remember, we can view tangent vectors as equivalence classes of curves. When we think of them as velocity vectors of curves, we can also view them as derivations, or we can think of them in terms of coordinate, local coordinate. So let's start with the viewpoint of tangent vectors as a velocity vector as equivalence class of curves. Recall that a smooth curve in M is just a map from some interval in R, some real interval, into M. Without loss of generality, right now we're gonna look at curves with domain of this form, from minus epsilon to epsilon. It then turns out that every tangent vectors can be thought of as the initial velocity of some curves. So let us review a bit what is the velocity of a curve. Well, on R, we can choose the standard coordinate t. Right, then, under a curve here is a smooth map, so we can push forward the tangent vector d over dt. At any time t0, we have this map on tangent space. So this image is going to be a tangent vector in this tangent space, and we call this the velocity vector of gamma, of the curve gamma, at time t0. We say that the curve gamma starts at a point P if P is equal to gamma 0, and the initial velocity of gamma at P will be the vector gamma prime 0. It turns out that every tangent vectors in this tangent space is going to be the initial velocity of some curve starting at P. This is not hard to see because taking a local coordinate patch, right, centered at P, we can just take this curve to be a straight line in the direction of this tangent vector. The idea is that at P, the manifold is flat locally there, and we can identify the manifold in the tangent space there just with subspaces of Rm. And we take a small enough curve gamma so that it's just a straight line segment there. Now, this allows us to view then tangent vectors at P as equivalence classes of curves starting at P, where two such curves are equivalent if and only if they have the same initial velocity at P. Under that viewpoint, we can describe this tangent space to N at P as just the subspace of TPM consisting exactly of the equivalence classes of curves such that one of the representative of that class has image lying in N. So let's see why that is, just to practice unpacking these definitions. Let's first prove this direction. So let's see what this statement is saying. So let's suppose that we have a vector v, tangent vector v in M here, which is the image of some tangent vector w in N. So it comes from tangent vector in N. Okay, and now we want to show that it must be the velocity of some curves coming from N. Okay, it's the initial velocity of some curves that is the image of a curve in N. And that is straightforward because from our previous discussion about velocity of curve, N curve, we know that this tangent vector must be realized as the initial velocity vector of some curve here. So if we take this composition, this gives us a curve in M and with initial velocity v. That's because of chain rule, because this vector, this tangent vector here is mapped to this, and under f this tangent vector is mapped to this. So that means that under this composition, this tangent vector is mapped to this. So this is the initial velocity of this composition curve. And so this curve does indeed come from a curve in n. So we got this direction. Now let's try to show the other direction. Suppose that this tangent vector is the velocity vector of some curves that comes from a curve in n. So it's an image of, so this curve is going to be the composition of a curve in n with f. So it factors through f. And we need to show that this tangent vector must come from a tangent vector in n, and that's also not hard to see, because now we look at the image of these this tangent vector, right, in under the map gamma, and we will get some vector w. And let's take the image of w under f, under dpf. Let's say that's v prime. By chain rule though, this v prime should be the image of d over dt under this composition, which we assume to be v. So v is equal to v prime, and thus v is the push forward of this vector w under the differential of f at p. Thus v does indeed come from a tangent vector in n. So a tangent vector in M come from n if and only if they are the initial velocity vector of some curve with image in n. So that's the first characterization. This works for both embedded and immersed submanifold. Next, we'll look at some characterizations for tangent space to embedded submanifold specifically.